Well, Stephen, that hydrogen is actually a very small molecule, and it's like a tiny ninja that can sneak into even the tougher of the materials and attack it and weaken it before even you notice. Hydrogen is regarded as one of the most important energy vectors that can bring us into the transition from fossil fuels to a green economy. We are turning a possible weak point into a strength point.
How do you maximize the longevity of a hydrogen container or a tank? That's what we're going to talk about today on Hyfindr Tech Talks. And I have an expert with me today, someone who has built a career around making cylinders, pipes, anything that you name it that has to do with storage of gases. He works for Tenaris, which is a company that has a whole portfolio of storage devices around hydrogen. I'm very pleased to be sitting here at Tenaris with Maurizio Bellingardi. Maurizio.
Thank you, Stephen.
Well, it's great to have you. And Maurizio, I want to find out today how to make a tank last forever. Tell me, why don't they even last forever?
Well, Stephen, that hydrogen is actually a very small molecule, and it's like a tiny ninja that can sneak into even the tougher of the materials and attack it and weaken it before even you notice it.
Okay, so even steel that we consider as being tough and durable and all of that, hydrogen can attack it. Okay, and where do we use steel containers to even store hydrogen? Tell us a bit about that.
Well, hydrogen is regarded as one of the most important energy vectors that can bring us into the transition from fossil fuels to a green economy. So, in this sense, wherever you are producing hydrogen or consuming hydrogen, somewhere you need a place where to store the hydrogen in while you're not using it. No. So, for instance, if you are producing hydrogen, like green production from renewable sources, or in refueling stations, if you have cars that are running on hydrogen instead of regular fossil fuel, or if you have a plant that is producing, let's say, e-fuels, so sustainable fuels coming from green hydrogen and carbon capture. In all these cases, you may need a hydrogen storage.
Okay. And why would anyone then use steel to store it? Because I've heard there are other types of storage ways as well, pellets or whatever.
Yeah, for sure. This depends much on whether you need, let's say, a lightweight and small tank. Probably you will go towards the composite cylinders that are made of reinforced plastic. So in this case, they are a very good solution. But if you need to store larger quantities, high pressure, and you don't care about the weight because you are putting the storage into a, let's say, fixed installation, then you will probably turn into steel because it's robust, it's affordable, it's reliable technology, and is less expensive than the composite solution.
Okay, so like the one you had here, you have the trailer, and actually I see we even have a bit of a model here. So this is how a steel hydrogen container would look like.
Yeah. This is exactly like a storage for roughly 2 tons of hydrogen is looking like.
2 tons of okay.
High pressure storage.
Okay, yeah, exactly. That's one thing I should mention, that you guys are actually working very much on high pressure. That's up to 1,000 bars.
Yeah, correct.
Like okay. So this, how much pressure could it take?
Yeah, this can take from, let's say, 200 bar to the, let's say, medium low pressure up to 1,000 bar. The geometry and the shape of the receptacle is remaining more or less the same. What is changing is maybe the material and the robustness of the construction itself.
Okay, so Maurizio, what does the typical life of this look like? I mean, when I look at it, I see steel. I think it should last forever.
Well, virtually the life of this steel pressure vessel is unlimited. There is no degradation over time because the metallic structure is not changing, let's say, with time. But there is a phenomenon that is called hydrogen embrittlement, where you have to be concerned about, because it's what we talked about at the beginning, with the hydrogen sneaking into and changing the material properties. Fortunately, this hydrogen embrittlement is, first of all, well known from many decades, and second, is not a feature of the material itself, something that you have within the material. It's always a combination of 3 different, let's say, aspects. One is material.
Yes.
The other one is the environment. So the hydrogen, how much pressure you are putting in, the temperature. And third, there is also the stress condition, so the operating condition. How much effort, how much stress you are putting into vessel.
Yes, yes.
All these three are important, and if you manage to get them well balanced, you can make this one last forever.
Okay, so let's go really deep into it. You mentioned it's the material that matters. So this embrittlement thing, can you tell us a little bit about it?
Yeah, sure. So let's use, if we imagine the metal like a lattice here of this mold sphere.
So this would be the
gray is
the gray exactly, and then on this side
the red one,
Okay.
the hydrogen.
Yeah.
The hydrogen sticks to the surface because it has high pressure, and it's so small that can dissociate into atoms and say diffuse into the metal lattice.
Okay.
And what is typical is hydrogen is going where the lattice is not perfect. So where you have voids or let's say lattice deformation, here you have the hydrogen. And what it does is reducing the material properties locally and also reducing the resistance to fracture propagation. That is the thing that is most concerning, and this is the thing that you have to take into account.
So that is the embrittlement.
Yes, correct.
So that means the hydrogen has gone in and, let's say, caused a bit of trouble or whatever. Or
it's like it's
now it's no longer perfect. So that is embrittlement.
Correct. It's like it's locally is changing your ability to let's say to keep the stress in and produces the local damage.
Okay. So when you're talking about the containers now, what kind of I know there's different kinds of steel that you can use here. Is there one kind of steel that's more resistant than the other?
Yeah, that's one point. We said before that hydrogen embrittlement is always a combination of three.
Yeah.
One is material, is where you have to look for the microstructure, the hardness, the strength, the homogeneity, the lack of small micro cracks, micro voids. The most of the material tends to be, let's say, perfect, or in the sense of the homogeneity, of the cleanness. The best is for the application, but it's not the only thing that you need. So we at Tenaris, we are, let's say, we know the recipe for making our own steel with the best properties to handle this kind of condition, but also we need to know the environmental condition and the operating condition to give our customers the best combination and the best product, not only the best material. Okay, I don't know if you.
So you have a bit of a, let me say, secret. Your secret sauce is to actually make the steel the way you make it. So if I asked you that, maybe you wouldn't tell me that, not?
Yeah.
But my question, Maurizio, is: so would you use different materials for different applications? So if I were a customer, say I want to build a refueling station, would I get different material from you than if I say I want to have a container for shipping or something like that, maybe?
Well, this is this depends much on say the combination of quantity, pressure, and application. For sure, we have different grades of the steel we provide for this application, and we tend to give a customized solution. But one thing is that you can see from here, this is a very modular. So one of those can bring maybe 50 kilograms of hydrogen at pressure. So if you need just 50 kilograms of hydrogen, you just need one. But if you need 2 tons of hydrogen, you make an array. And so we don't change much the material because we just replicate to make a modular structure. So this is one possibility, or this is another one. You can see you can stack more than the ones you see in the picture, or you can put them aside. And so it's very flexible. Like
I see that there are even, like, let's say, units of 4 that get stacked in different ways. Just one thing, the pressure, does the pressure matter? So just coming back to this now, you have the molecules. Is there, like, is there a difference if they're just, let's say, relaxed on one side, or whether they're all like sitting here at 900 bar?
Yeah, here it's definitely important. the point is that you have two aspects that are dealing with it. The pressure, absolute value, the highest the pressure, and the worst is in terms of hydrogen tendency to diffuse into the material and create problems. But the other thing that is very important is cycling the pressure. And now I will explain you why if you give me the opportunity.
Maurizio, I know you're going to come to cycling in just a moment, if you don't mind, but just about this, you say one is the diffusion and the other one is the pressure. Does the diffusion increase when the pressure is higher?
The tendency of the atoms, hydrogen atoms, to dissociate on the surface and get into the metal is increasing with pressure.
Okay. All right.
Definitely,
Okay.
yes.
Perfect. Okay. So now, the second thing I wanted to look at is the actual design of it. So, I mean, we've seen Swiss clocks and things like that. They look very complicated, but when I look at this, it looks either genius or very simple. So can you tell us a little bit about the implications of the design here?
It is indeed very simple.
Yeah.
This is a consequence of one of the driver in the design.
Yeah.
In this case, you need to know where the hydrogen is going to make the most damage.
Okay.
How you do that? You modelize you make a virtual model of this. You put virtual hydrogen in, and you see where is the most critical section. So where you have the most probability of having a failure due to hydrogen. And knowing that, you correct it, you put proper countermeasures by removing defects, conditioning the surface, raising the wall thickness to reduce the stress, all these kind of engineering things that bring you to a better one. In general, we have to say that this geometry you see here is a long cylindrical shape with smooth transition towards the ends, like with this dome, is made on purpose to minimize any kind of abrupt change of thickness. So you have a very smooth transition of stresses. This is lovely for having, let's say, less problems in the fatigue and longer life.
Okay, so I just want to say very clearly that oftentimes it is genius that looks so simple. You know, I think it was Steve Jobs or whoever was that said it. You know, it takes a really long time to make a simple design that is perfect. You know, so I think it's all the more compliment to your design if it's that simple. And you say so. One of the guiding principles is to reduce the stress and make the transitions as smooth as possible. Do you have welding on this then?
No, this is one of the feature of this kind of receptacles. We don't use any weldment, because weldments are known to maybe creating problems, because we saw hydrogen loves to go where the structure inside the metal is not perfect. And weldments are, kind of metal that are put together. And even if you have the perfect weldment, there is a discontinuity, and hydrogen loves to go there. By removing completely, so having a seamless receptacle, in this case, a seamless pressure vessel, we are turning a possible weak point into a strength point.
All right. Okay. So it all goes in. But how do you then, if you don't weld it, how do you make it hollow and get that form? By bending it, or you mold it into shape?
It's a hot forming process.
Okay.
So we start from a steel bar we cast ourselves. Then we turn the bar into a hollow using the seamless tube rolling process. It's a hot process at the same. And then we close the ends, or literally we almost close the ends with this smooth transition using what is called a spinning process. It's a hot forming that is
You're reducing that by a step.
Yeah, correct.
Right.
So it's a well-controlled and let's say, smooth transition without using any weld.
And it's a single wall, not a double wall.
It's a single wall.
It's a single wall. Okay, cool. Right. Okay. Now let's go a little bit into the operating situation. I know you wanted to talk about the cycling earlier, so maybe we can talk about all of that.
So I was saying that, first of all, we need to care about failure. Okay. We don't want this kind of thing to fail, because it's a pressure vessel, so it releases energy, because it's hydrogen, so it's flammable, and we need to be very careful about that. How material is failing? There are two ways of failure. One is you simply overcome the tensile strength. Imagine you have, let's say, a rod of metal, and you just pull it as much as you can until it starts to deform, and then it suddenly breaks.
So just as a liberation, we have I've seen this, and we have another video about this where we actually pull. This is a test sample that gets pulled, yeah. And I like Maurizio, so this was your idea to bring this in, to have like the chains being pulled apart. Yeah. Like
This is to give you.
you have someone at Tenaris who can do this.
Yeah.
Full chain.
This is to give the idea. Okay, until I apply a force that is not enough
Yes.
to break it, it will never break.
Okay. All right.
So translated into pressure vessel.
Yes.
If I put pressure in my vessel here,
Yeah.
and this is low enough to not overcome this tensile stress, this will last forever. Okay?
Right.
But unfortunately, pressure vessels are working another way.
Yeah.
They are working much lower than this, for sure.
Yeah.
But they are working, repeating
Okay.
the stress. So it's like bending continuously the steel rod, or like in the example I put here, like trying to sewing. So step by step, you apply small effort, but the steel will become weaker and weaker step by
Over
step.
time.
And why is that? Because your pressure vessel is operated by emptying and charging over time.
Yes.
This is how they work.
Yeah.
If it is, let's say, you need hydrogen, you take it from the storage. You don't need hydrogen, you put it on the storage. So it's always like this. So we need to think about what does it change in between the two failure modes.
Yeah. Okay.
Unfortunately, hydrogen is doing its job more in the fatigue, so in the second, let's say, failure mode, than in the first one. So it's not actually changing that much the tensile limit. So if you have, let's say, your robustness here is, you put hydrogen, is not that much changed.
Yes.
But in regard of the fatigue limit, hydrogen is actually reducing it much.
All right.
And
So if the container were just for using it once, it wouldn't make much of a difference when you're using it hydrogen. But if you keep filling and emptying, filling and emptying, filling, that their hydrogen makes it more difficult for the
Exactly,
container.
exactly.
All right. Okay.
And why this is, let's say, tricky, because this is very easy to predict.
Yeah.
You have one limit,
Yeah. You just know the pressure.
but this is much more subtle, because this limit is much more difficult to be determined, and when hydrogen comes into play, is even more difficult to be predicted. So
Understand.
this is where, let's say, all the testing that we do in Tenaris with our material in hydrogen to assess what is this effect of accelerated, let's say, failure because of the hydrogen comes into play.
Okay. So what do you then actually do? I mean, so okay, now we've understood this. So that means you try to limit cycling, or what do you do?
Yeah, it's coming back to the hydrogen embrittlement triangle, or let's say the material we choose the best, the environmental condition the customer is choosing, pressure and hydrogen quality, we only need to limit the operational change. So what we do in this case, and I would like to bring you an example.
Yes.
First of all, it's important we understand that cycling is, let's say, the amplitude of cycling is on the essence. So let's imagine yourself is the pressure vessel, and you are going to the gym, and lifting weights is your daily job. So you're working out, and as the pressure vessel is loading and emptying, you are lifting a weight. If you lift a weight from the ground to up above your head, you are doing a full
cycle.
So you do a lot of effort.
Yeah.
And we call it, say, full pressure cycle. It's hard because you need a lot of effort.
Yes.
But you can operate the vessel, or you can do gym another way. So you can do half a cycle. So you just, let's say, swing from your belly to up above your head. No, so it's you do less effort, and you do less gym, but it's another way to work. Or you can do a shallow. So you just swing just a little bit, okay? So these are the way you can operate a pressure vessel.
Okay.
Why this is important? Because the effect on the amplitude, the effect of the amplitude on the life, on the fatigue life, is non-linear. So a small change in how you operate, in how you do the gym, is doing a lot of difference in the total life. So you measure fatigue life in cycles.
Yes.
How many cycles can I do?
Doing the whole
doing
thing.
the whole thing.
Yeah,
Okay.
yeah.
So let's make an example to understand.
Sure.
We have one vessel, 1,000 bar design, and each one of them is keeping in 25 kilograms of hydrogen. Your job is to deliver 50 kilograms of hydrogen each day to your user. No? And you can do it easy. Okay, you empty and charging every day. Okay, you have to do twice.
Yeah.
25 plus 25 makes 50.
Yeah.
But this, if you do the fatigue analysis, this gives you 2,000 cycles, and then you have to stop for reinspection before you can continue operation.
Yeah.
So 2,000 cycles, if you do it twice per day, so it's just less than 3 years. So not that much. But you can operate, I say, half cycle. So you just deliver 12.5 kilograms each swing, but the fatigue analysis tells you that you can do not the double of cycles, but 16,000 cycles, 8 times.
Okay.
So you reduce half your effort and you get 8 times the life. So in this sense, it's no longer less than 3 years, but you can swing this way 11 years.
All right.
So it's very important that the user understand that if they design their usage of the storage in a way that they minimize the amplitude, of course, compatibly with the need of the user.
Yes, yes.
If they reduce the amplitude, they will get much more life than what is the actual reduction.
Yeah, and I see it's even getting more here, from 11 years to 103 years.
Yeah, in this case, we just reduce another half.
Yeah.
So instead of delivering 12 kilograms of hydrogen each swing, we do, let's say, 6 point something. So you have to do 8 times a day.
Yeah.
But since the cycles are now 300,000, and you do 8 cycles per day, you get to over 100 years.
Okay, but Maurizio, so just in my little math, this means, but if you read the 50 kilograms, so you could use 2 tanks then maybe, so that you have more volume. I mean, your investment would be higher because obviously you need 2 tanks, but then you reduce the number of, let me say, the cyclic load on those tanks, and then those ones will last you 8 times.
This is another possibility. Of course, if you increase the number of tanks, you can cycle the same and deliver the double. But of course, you have to invest more money because you need one more tank. But so it's a combination of
exactly. But basically, you have to look at the way you use, because I mean, maybe the user wants those 50, and then you have to talk and find what the optimum is.
Sure. They have to simulate all the, and Tenaris can give them let's say the tools, the guidance, the guidelines to do the better job.
Okay, so that's the kind of thing you would do.
Yeah, sure.
For example. Okay, cool. So Maurizio, you said we've understood pretty clearly that this cycling affects. Imagine now I have only this option to go, and at the end of 2.7 years, I have to stop now. What happens?
Okay, it's you have to stop your operation.
Yeah.
You need to call an inspector, depending on the regulation you are.
Yeah.
And this inspector has to perform a set of, let's say, looking closer to your receptacle, to your pressure vessel, to assess if it's suitable to continue operation. Okay.
All right.
So we are talking about fatigue in hydrogen. So the inspection is normally, let's say, involving a close look to defects. Okay. So you have some kind of different technologies that can do that, and we can. Of course, visual inspection. The eye is the first one.
So if we have this, for example, so like this has run for either 2.7 or 30 or however long it is. Now it's time for the inspector. The inspector comes and looks at it from the outside, obviously.
Yeah.
And what else do they do?
Well, the visual inspection is from the outside, obviously from the inside as well, because
They also look
both
in.
ends
Yeah.
can be disassembled,
Yeah.
and with an endoscope you can go in and take a look on the.
Can they find out if there's embrittlement?
Embrittlement, no. Embrittlement is a microscopic phenomena you cannot best see, but they can find if there is a macroscopic defect going on.
Yes. Yes.
To get microscopic defects, you have to use one of those acoustic emission pressure tests or ultrasonic inspection. They can be done on the cylinder on site. It's just you put microphones here and here.
Yeah.
You put pressure in, and while the cylinder is inflating, the microphones hear if there is any active crack that is propagating. And they
What's like wood cracking or something?
correct, but every material has its own frequency of cracking, so you know perfectly if there is a crack or it's just a noise.
Yeah.
And it also, by triangulating the two signals, it tells you it's here, it's here, it's here. So you go there with an ultrasonic probe and you just look for it. And when you find it, you measure it, because you can do that. And if it's critical or not, it decides if the vessel can continue operation or it has to be repaired or segregated.
Okay. So that means when you have a set like this, you inspect all of them, and it could be, let's say this one is, you find some problem. What happens then? Do you have to take it out and wait?
Basically, you take it out,
Yeah.
and you can, if the defect is very shallow, you can repair it.
Yeah.
It's very simple operation. Then you can retake into service. Or if it's a big defect, you have to segregate and replace with another one.
Okay. So that means best is right from the beginning, plan how this is going to be used so that you can plan for your entire operation.
Yes.
That the tank can do.
Yes.
Okay.
By the fatigue analysis we can provide to customers, and their monitoring day by day what is the usage, they can predict when the let's say the damage would be let's say close to the limit, and so to plan the inspection. This is on the essence, because this can save a lot of money and time in operation of these vessels.
Okay, cool. Maurizio, so wow, we have really covered a lot here now. So can you just summarize this again?
Yeah.
So if I have a container now, I bought this, what do I need to do so that it lasts as long as possible?
Yeah, I think we can summarize into 4 steps.
Yeah.
First one is select the storage option that is actually fitting you.
Okay, that's it. So even before I buy, think about
before
it.
you buy, you talk with me, and you tell me exactly what you need.
Okay, and then
I will tell you exactly what you want to buy.
Okay.
And second one is, once this is in operation, you have to carefully monitor. The more carefully you monitor, you don't have just to count cycles, because as we said, the cycles are not all the same.
Yeah.
Shallow cycles are less problematic. So you have to monitor pressure, temperature, and so on to keep your records. And this is good for optimize, because you can predict and you can set your inspection times and your inspection activities years before they happen, so you can minimize your downtime and spend less money to do that. And that's it. I think it's all you can do, all you have to do to, let's say, maximize your lifetime and say care about your safety and your productivity of your storage.
Yeah, and then obviously I think if you're monitoring, you can also, let's say your plan can vary accordingly. So if you see that you're, for example, you're using the vessel more than you plan, okay, that's
Totally dynamic. I mean,
exactly.
Maybe one year is different from another. So, but this active monitor actually allows you to, let's say, to figure out if anything is changing, and so you have to predict to set your inspection before or after. So, yeah, that's,
so that's actually
a good point.
I mean, and even without the inspector, I already know basically what I'm trying to do is avoid trying to prolong that process as long as I can. And just looking out into the future, Maurizio, are there any changes? What are trends? I mean, you've been in this for a while. What are trends that you're currently seeing in this area?
Obviously, this is one of the critical stages into the whole chain of the hydrogen. No?
Yeah.
Storage is needed, and the future trends will be to reduce as much as possible the cost, not only the initial cost, but also the operational cost of this solution. I don't expect actually a revolution in the shape or in the material, but I would expect that to get, let's say, putting together manufacturer, users into, let's say, a round table where to optimize the solution, because it's not good to make something that works for all the options.
Okay.
It's good to have customized, because you need to reduce as much as possible your investment. Try to overbuild is not always a good idea.
Okay.
Buying a vessel that has infinite fatigue life is not necessarily needed, because well, yes, you maybe remove a problem, but you will not use your plant for 1,000 years. So yeah, it's a compromise, but the future is to take the compromise to something that is sustainable, which is what we are actually doing with our site.
Well, beautiful words at the end. And I started by saying forever, but as you see here, maybe it's not even needed forever. So you actually can do a good job by just planning for the time that makes sense.
Yeah.
Maurizio, this has been an absolute pleasure. Thank you so much for sharing so much insight and how to help us make hydrogen storage last for as long as we need.
Thank you, Ivan.
Thank you very much for watching. It's been an absolute pleasure. And if you're looking for storage containers or things like that, come onto hyfindr.com. You can get into contact with people like Maurizio. And if you like this video, give us a like. And there are many other videos to watch. Thank you for your time. And thank you again.
Bye-bye.
Thank you. Bye.